Hello, welcome back to the second to last algebra, geometry, and trigonometry video. I will be your host, as usual. I also got a new marker board. I found that, I think it was in a garbage can. Well, not really a garbage can, more like this, just on, it was a garbage can. But, I kind of like the marker board. I mean, I didn't really care that I got it out of it. All I know is that I washed it off and then I'm using it now. So, I'm going to start cutting out the video for this one only into sections involving the parabola, hyperbola, and the ellipses. But first, let's go over these conic sections. A conic section is just the section of a cone. So, from here, by the way, I just realized I forgot what I was going to say as I was saying it. But, this is a little diagram, of how, the conic sections actually create these shapes. So, you have the circle, which you can put down to any level on the cone. And it'd make you really think, can you do it with the others? Well, yeah, you can. So they have separate equations, and you can see that they change based off of this D. But before we go ahead of ourselves, let's just go over the shapes that we're going to talk about, because we already covered the basic shape of a circle in earlier videos. And you know, it follows the equation x squared plus y squared equals r squared. And you can center it, or find the center of the circle by equaling them both to 0. Well, the thing about this one is that you can do the same exact thing. But let's talk about these three shapes. We're going to start with the ellipses. Just a little overview real quick. The ellipses is like this oval thing, and it'll just kind of exist. That's all I can really say, because it can exist on an x squared or a y squared type of graph. And it will always have this oval shape, and it's actually an important shape. The reason being is that it's the solution to this 300-year-old problem called Fermat's last theorem. Involved this thing called a modular elliptic curve, where basically the shape wouldn't be able to be anything if it were past like y squared or x squared, because it involved the Pythagorean theorem. I mean, I could start talking about it, but I'd rather talk about what the shape is, and I don't know, maybe I could do like a follow-up video. So, the next one I'm going to be talking about is the parabola. And this one has like a shape that's half of a football field. Wow, that was so American of me. And that's all it really does, and you can switch the distance, which I labeled D, to increase where the focus point is. And I will start talking about that, but just know that the hyperbola and the parabola can sort of be mixed up if you look at it in conic sections. Sorry, I just blanked out. But, so the hyperbola, it's a little different from the parabola, but kind of follows the same thought process, and it basically follows this method. So, it's like two parabolas, but they're like facing away from each other. That's how I can describe it. And this stuff isn't really too complicated until you get into like multivariable stuff, where you go into like 3 dimensions, 4 dimensions, 5 dimensions, just whatever. And it kind of leads up to that once you get into like imaginary stuff, when you're talking about multivariable stuff. But let's continue on. So, for the first part of the video, I wanted to talk about parabola. So, a parabola is just a shape that's always going to be like this. It can be on the x-axis or the y-axis. So the x-axis, you know that it'd follow that if you see that your x variable is squared. And you know that it will be like this when your y variable is squared. Because if it's squared, then it can be both negative and positive. So it will start reflecting. And it's quite simple to spot, because you see this in quadratic stuff. Or just a basic x squared graph. So, because this is the equation for a parabola. When you have an x squared graph, what it means is that your d is going to be a quarter, which then will turn into 1, so y equals x squared. And then you end up with a shape like that. And you know that it's never going to be positive, so I'm not talking about like these are the same shapes. I'm just showing you that they're the same equation. You just have to know how to use it. And these... Here, let's a little backtrack. So these d's are kind of important when it comes to how the shape will look. So you have d over here, which is the distance from here to the focus point. If you actually take notes on this stuff, I would probably write that down. It's called the focus point. And the focus point is the distance from the maximum or the minimum of the graph to, the focus point. It's kind of weird. So, now we have this part where it's a negative d. And at that negative d, it's called a directrix. I'll write it down for you. It's weird. My handwriting gets worse and worse as time goes on. Whatever, a directrix. I think you can read that, although I am a little stupid. So, now that we know how it works on the x squared, why does the y squared do that? Well, the same reason why it reflects on the x squared. Because whatever y value you get for that, you can reflect it over because it's squared. And although most of the time it should be an independent variable, you can still square the independent variable. Because if you take the square root of hold up. We have a little issue, because I just realized that the letter I used sort of relates to something called an infinitesimal. And that, I don't want to mix you guys up, so just to use any random variable you want, as long as you know that it's the distance. So, because, you can take the antiderivative of that and it'll turn into like just 4x, and then that'll be like y cubed over 3. Yeah, I don't like how I wrote that. Oh, whatever. So anyway, let's see. When you know that there's a dependent variable, you know that the square will turn in negative and positive. Well, you could do the same thing with y to the 4th or y to the 6th, because it will keep alternating from positive to negative. And you can test me on that by just using the example of negative 1. Negative 1, 1, negative 1, 1, negative 1, 1. So what we do know is that as the exponents get bigger, it will get larger, but it will keep alternating back and forth. And you can plug in two numbers into the even integers. I think I spoke about that in an earlier video. So that's the only case where that happens. If it's an odd integer or if it's not even, then you can't do it. It's just as simple as that. And if you want, you could prove it yourself. You know, you just have to figure out how to prove it all the way to infinity. Or into the uncountable infinities. So, let's just put down n squared and n being an element of dependent variables. I'll put dep var. So when you know that it's n squared, n being an element of dependent variables, then you know that it's going to most likely take these shapes. And you can see these shapes in 3 dimensions, it's just that it depends on your frame of reference. But I shall go backwards. So let's talk about the vertex. You can find your vertex whenever you set a variable equal to 0. Like over here. I think I'm teaching this right. Just one moment. Yeah, so anyway, wherever it's 0, that's where you'll find your vertex. So your vertex will end up being wherever both variables are equal to 0. So right here, it will be at 0, 0. But what about if you use a transformation, like x minus some random letter k? K being any number. Or y minus some random h. Then wherever that is, wherever that 0 is, that's where... Why do I keep blinking out? That's where our vertex is. Alright? And normally it's a lot easier to deal with parabolas than it is the other shapes. But I don't think these shapes are too complicated. You guys can probably grasp onto the concept. Because you can find your focus point wherever you're... because you'll be dealing with shapes based on whatever the dependent variable is. So you set... Here, I'm going to tell you something. You set that to 0 if you're trying to find your focus point. And you find wherever your x plus d is. That's all it is. Did you catch on to that? Alright. So that'll be the equation, and if it's the other way around, then you do it y plus d, and then it's x equal to 0. Oh wait, I meant y equal to 0. Make sure it's equal to y. So like if you have a transformation from y minus h, then the coordinate will be h. I hope you got that down. If it seems a little weird how I kind of explain it, I could probably upload the paper I use, and because I write down just in case if I forget stuff during the lesson, because I don't want you guys to forget whatever I'm trying to tell you guys. If you want, all right, I'm gonna go on a little tangent, and not the type that goes across the circle. So I was thinking about it. If you guys need me to come back to like a course, if people really want it, I will create assignments. It doesn't really matter to me. I don't have anything to do. You know, if you need to find parabolas, hyperbolas, ellipses, or even just assignments all the way back to linear equations, it doesn't matter. I will write those assignments. Because I do want you guys to learn this stuff. I'd rather you guys be logical than illogical. Because mathematics is founded on the study of logic. But anyway. And unless it's a science class that you want me to write assignments for, I'm not going to apply any of this. Like, it just doesn't seem really anything to me if it's a mathematics course and I apply it. Because it just... I like the ideas of this stuff. I don't really like actually applying it. It doesn't make me interested. But yeah, that's pretty much it. Yeah, I believe that's everything I needed to talk about. So that those two will be the equations for getting a parabola, and you know what they look like because I corresponded them to each graph. And now coming up, I'm going to work on hyperboles. So, just 1 second, and alright, let's continue on with hyperbolas. So, hyperbolas are going to be this shape right next to the parabola. The difference between a parabola and the hyperbola is this thing right here, because it still has the focus point, and it still has the same curve. Oh, by the way, I forgot to mention for parabolas, the vertex was not the center. The center is just the center. The vertex is going to be this point right here, the maximum point, let's just say that, of the graph, or the minimum point, depending on how you look at it. Because you might think that this would be a minimum point and this would be a maximum. But I just want to get that like straight to you. So now I'm going to start talking about hyperbola. So it's composed of this type of thing right here. So it has this formula, and it will switch between if you want it this way or this way. Wow, I completely butchered actually saying words. But when you see this formula and it's x squared over a squared, then that means that it should be going in this direction. It should be like that. And it will have these components that start turning rectangular. So you have A units going right or left, and then you have B units going up. And as you trace along, it will turn into a rectangle. And the reason why I drew those lines is because these, I didn't draw it very well, but these are asymptotic to those lines. And if you know what asymptotic means, it means it's just not going to touch that line. So it's 10 o'clock at night. Okay. Oh my goodness. I'm just going to continue on. So you'll have these asymptotes, and this is going to be probably the first time you've seen a slant asymptote, and it will go this direction, and it will have the same thing going on over here. And just remember, it's going to look rectangular most of the time when you deal with hyperbolas. And when you're trying to find the center, just equal both of them to 0. That's pretty much it. And if it's like x minus h, h being some arbitrary number, and same with y, y minus k, y plus k, x plus h, it will just be centered around that. So when you're trying to cancel out x plus h, it would be negative h. So it would be negative h some point on that side. Or for the y, if it's y minus k, then it'll be some k, so it'll be centered around here. I kind of messed up the lines right there, but the idea should be pretty simple. And then you have this one, and it's the same idea to find the vertex. And the thing is that I placed this third component called C. And I don't really want to talk about the derivation leading up to that. Just know that it'll follow this formula to get the focus. And depending on how the graph looks, like for this one, then you set x equal to 0. And all you have to do is just find your C, and then boom, you get it. And it will also be a negative C. Now, I want to start talking about how to get the lines, because, here. So when it comes to these lines, you have to remember that it's going to be plus or minus, because it's going to be asymptotic to both sides. And when you're doing that, it should come out to m equals b over a. Or at least I believe that it should. Here, let me just check for a second. Alright. So that'll be plus or minus b over a. No, wait, not that one. It's going to be in the linear equation. So you set it to where it's y equals mx, and then some b, depending on if you have some shift. And if there's some shift, then you know that you can follow this equation where it's y minus y0 equals m times x minus x0. And that's how you'll be able to deal with that. I think I wrote down that equation earlier in the videos. But if not, it's going to be y minus y0 equals m times x minus x0. And remember that it's plus or minus on the m times x minus x0. X sub 0. My bad. Alright, so once you know that, all you have to do is just circle it around the center, and the lines should cross at the center. And then once you do that, you'll be able to draw your hyperbola pretty easily. And then you just have to find your focus and whatever. Alright, so I'm going to cut out the video now, and we're going to start talking about I was about to say epilepsy. Ellipses. Alright. Alright, so we're on the final thing now. So this is what we call an ellipses. It's like if you brought together two hyperbolas into just an oval. You can see it right here. So instead of it going away, it connects. So right now I just have the vertical part of the ellipses be the longer part. So the A would be focused on the y-axis, which I did write down right there. And then for this one, the A is focused on the x-axis, and that's why that has the longer part. Just assume that the A is the longer part. So, and if you get a worksheet, and it has like A as like 2 and B equal to 5, just treat it the same. That's all I can really say about that, but alright, so you have the components A, B, and C again. And you have your equation at the bottom, c squared equals a squared minus b squared. So your C is where your focus is, or the distance from the center to the focus. And then you have your A, which would be the distance relative to the y-axis. So you can look at the equation and y squared over a squared, and that'll come out to that. So, is there really much to talk about? I mean, you know that B is related to X in the first case. Honestly, ellipses isn't too complicated. Just know that there will be times when it will be factorable, and then you'll have to change up how the shape looks. Or if it's centered around like X minus K, or Y minus H, as I've been using for the last couple of times. I'm starting to like get drowsy just talking about this. But just remember that these equations all apply to ellipses. And depending on how you guys react, maybe I need to do some proof-based courses, because that would actually be a bit of a jam. I kind of enjoy doing proofs. But anyway, so the major, the thing I wrote on the first diagram, the major is actually related to the vertical axis. The distance from the origin to the center to the maximum or minimum parts. So like, let's say your A was equal to like 5 or 6, then I'll just choose 6. You would have a major going from 6 to -6, assuming that your center is at 0, 0. And the same thing with B. It would be B, -B. It follows the same method as we've spoken about before. And you can continue. I believe you can continue the equation. Actually, no, you can't. That's only if you add another variable. So I'm pretty sure that's it. Yeah, I didn't really like recording this video, but I don't know. Maybe you guys got something out of it. So now we know how conic sections work due to analytic geometry, and where the circle will appear, which it can appear in like cylinders and crap. It doesn't really matter. It's also the reason why we can derive volume using the circle. And then you have the ellipses, which is basically just hyperbolas connected. And then you have parabolas, which is just a giant portion of it that just appears. And you can increase the distance depending on how far away it is. Or, because right now I just have it close to where the hyperbola is. So probably the best thing you can do is just make sure that it doesn't turn into an ellipses with the parabola, because if you extend it past the midline, then it's just going to start looking like an ellipses, and it won't really help anything. And, is there anything else I need to talk about? I don't think there's anything else. Well, thank you for watching. I'm sorry I've been a little late. I keep forgetting to upload. I'm not really sure why. I just gotta, like, sit... Because for some reason I have this issue where I sit down and I just forget everything. So, that's pretty much my best excuse. But, I really want to get these videos out. I enjoy, recording videos. I even skipped a couple of videos last time because I completely forgot. So, I'm going to try and get right on top of it. But otherwise, that's pretty much it. God bless you. See you in the next video.